All right. Thank you very much. Thank you very much also for the invitation. Um, Great to be here. I wanted to give you this morning a brief introduction of what governs the structure formation in the universe. And I think in a nutshell, we could say like, okay, the matter in the universe evolved from a homogeneous soup into a like highly structured entity. And so what I'm going to cover in this talk, or what I want to talk about is what seeded the large-scale structure formation, and how did stars and galaxies roughly form, and how do galaxies evolve over time, and even can galaxies affect the large-scale structure? And let's dive directly into it. So when we start from, maybe I should go back here. So if you look at this picture, you have basically here sort of the Big Bang, and then the last surface scattering, the cosmic microwave background, I think about which we were going to hear a lot more today. So I'm not going there into detail. So this is basically, I will treat this as my initial conditions. And basically then you can see how the structure evolves throughout the universe. So we will start at the very beginning, at the cosmic microwave background. And basically what that gives you is sort of the initial density perturbations. So you will have some, maybe here in blue, like slightly underdense regions, or you have some overdense regions. And I mean, today the cosmic microwave background has an average temperature of 2.7 Kelvin, and the fluctuations are really small. And more or less also the fluctuation field is roughly Gaussian. So how do we form structures from this? So this is something, for instance, Seldovich thought about. And so what he was thinking about is like, if I have a mass particle in this density field, and I have a certain velocity field that comes, for instance, like from my gravitational field, where does this mass particle go? And that's basically what he computed. And so then you can put together sort of like a mass flow tensor. And this then eventually defines actually structure formation in a certain way. Because I mean, what you can think about in the 3 different dimensions, you won't have the same mass flow. It will be slightly anisotropic. So what will happen if you have what you see here on the right-hand side is first you have this whole volume, and then you start collapsing in one dimension, basically. And you form what we call wall sheets, or I think it's also referred to Seldovich pancakes. Then you collapse in the next dimension, and you form filaments. Eventually in the third one, and then you form clumps and nodes, and that's basically where the galaxies also will start forming. And maybe to give us a better idea, so here it starts like pretty much in the dark, but here you can roughly see what's going to happen. So you have a pretty homogeneous gas cloud in the beginning, and then you start seeing first sort of the sheets collapsing in the filaments, and here now you already see the first filaments approaching. And the key thing about gravity is also that it has long range, and it basically introduces hierarchical structure formation. So what do we mean by this? So hierarchical basically means that you form small structures and they progressively form larger structures. And I think this is what you also can see. You have, for instance, like a lot of small filaments, but then you have these large filaments starting to form. So there's a basic hierarchy in this structure formation. And the whole structure that you're seeing now, basically this entity of sheets, filaments, and clumps or nodes, is what we refer to the cosmic web. So I think it also looks a little bit maybe like a spider web. Well, not really, but yeah. So that is our cosmic web. So this is basically one of the first really big simulations that were run. So if anyone is interested, that is called the Millennium simulation. It's from, I believe, 2005. And yeah, so you see like in the end, you form this like massive dark matter halo where you have a lot of small stuff circling around. So observationally, what have we seen? Can we see this cosmic web observationally? Can we actually observe it? And the answer is yes. So this is what people have done. They have used the Apache Point Observatory and conducted a large survey, which is referred to the Sloan Digital Sky Survey. And what you basically see here from the center to the outside, that's what we call redshift. So this is if you go further and further away from the Earth. And basically the redshift tells you like how much your wavelength is being shorted in a way if you go to further redshift as the universe has been expanding. So this is basically our distance or time measure often in cosmology. Yeah, so as you can see then so this shows you the distribution of galaxies, and you can very well see that the galaxies follow this cosmic web filamentary structure. So in that way, that seems to work really well. Then if you go from the filamentary structure, we actually interest like in the galaxies that we actually see. So how do those evolve? And the galaxies normally evolve like in what we call the dark matter halos. And the dark matter halos are basically the clumps in your structure. So up to now, before these simulations which I showed is mostly just looking at dark matter. And if you look at dark matter and then you ask yourself, okay, how do the number density of clumps evolve over time? Which should give you an idea like how do the numbers and sizes of galaxies evolve? And so in the beginning, everything will start with a roughly low mass, and we will only have a few fluctuations. And if gravity starts working, the initial fluctuations where the first low mass galaxies form will become more and more massive as they attract more and more material. But as the universe more and more expands, more small scale fluctuations will also appear. So you form more and more small stuff. So in the end, you basically move, your galaxies grow in size, but they basically also grow in number on the low mass end. So basically, yeah, as we go in time, we get to see more galaxies and also more massive galaxies because they become more massive. So that's a simulation, for sure. I mean, these are quite high redshifts. So I would say, so the points are probably the simulation measurements, and the other one are sort of analytic fits to those. All right. So now we get an idea that if we have a dark matter halo, it grows in mass over time. So it accretes matter over time. So, but what does happen to basically the baryons? And so what you can imagine then, what it roughly looks like, I mean, this is just a sketch. You have this dark matter halo, and you have sort of, it's connected mostly to the filaments. And what you will have is that the gas will follow the dark matter. And so now you can imagine you have this dark matter halo, which is heated sort of to a virial temperature. You have a cool gas, which comes from the filaments. So as it hits sort of the dark matter halo, I mean, it's very, it experiences a shock. The gas is heated to the virial temperature. And actually, I mean, if you look at the dark matter halo, only in the center you have the galaxy. So now the question is like, how do we get the gas to the center of the galaxy in order to cool and form stars? Yes. Sorry? Yes, yes, yes. Just via gravity. There's no interaction otherwise. And the way this happens is basically it cools radiatively and slowly then drops or folds onto the center. And yeah, so this cold accretion, how we've referred, is established after a few tens of million years. And then you basically have this cool gas with which you can start to form stars in a galaxy. So if you zoom then into the galaxy, the actual way how it happens is like, you won't have like one homogeneous soup, but you have actually a very turbulent medium in which you have clouds. So in this case, they're cold molecular clouds. And in these cold molecular clouds, you will form stars. So basically, the interstellar medium, how we call the medium within the star-forming region in the galaxy, is very turbulent, has some hotter components and cool components, and basically have here the cold molecular clouds where the stars form. So if you go then into one molecular cloud, this is basically where then the collapse starts, and this gravitational collapse is only possible because you cool then also again radiatively by releasing the thermal radiation. And so this continues, and at some stage you basically form a protostar. And this protostar will keep accreting material from the surrounding. And there are various physical processes that can affect like how much mass you actually can accrete onto the protostar. So for instance, these are like protostellar jets. Then of course, the radiation from the protostar itself, but also winds that are launched from there. So all these processes basically affect like how much mass the protostar can then accrete, and actually at some stage form a main sequence star, which are the stable one which shine for a longer time. So if you look at the main sequence stars, there's a variety which then evolves. So I think this is, you form various stars of various masses. And I think the key point to take away from here is like you have what I call the low mass stars, which will are like our sun. They will last like, I don't know, a billion years. And then you have the more massive stars, and particularly in my research field, it's very interesting, sort of the type 2 supernovae. So if you're more massive than, say, 8 times the mass of our sun, what happens, these stars are so massive and so luminous, so they shine more in the blue because they're far hotter. They only live like for 8-10 million years, and then they explode as supernovae, and yeah, different types of supernovae depending on your initial mass. And that's basically sort of the key point as a feedback mechanism. When you form stars, you form a certain population of stars, and that will change also the gas from which you have formed. And maybe to give you a sort of an idea how this could look like in this interstellar medium. So this is basically a cloud where stars are going to form. According to the colors here, I believe red is the sort of the density, and I think the blue is sort of the velocity component. So it's a mixture between density and velocity. What you already can see, I mean, you see forming again like these sort of filamentary structures. So that's very similar to what we saw on large scales. And then you form the first stars. And I think then it takes a little bit while until you see sort of these stellar feedback processes coming into action. For instance, what you're going to see is the protostellar jets, when they come, and once they explode, you can also really see all these. Here, for instance, you see then, I think it's probably going there now. Yes. So you can see now the protostellar jets, like the effect it has on the whole gas distribution. So it becomes really turbulent. And therefore, it's also really hard to simulate or make predictions because you have a various amount of physical processing interacting with each other and really being dependent on what you assume for the other physical process. So, I mean, as you can see, it's very violent. Yeah, and then you can see also up there, I think, stellar winds. And at some stage, you also see sort of when the massive stars explode at supernovae, they basically really carve out, they blow out the gas, and you have not much gas left around the stars. And you can see, yeah, the cloud already starts like nearly to dissolve. There is not so much gas anymore close to the star forming region. I think when it turns now, that's what you can see. Yeah. So this is just to give you a rough idea, yeah, how the interstellar medium looks like. This is one of the most up-to-date simulations to my knowledge. So yeah, they have included really like most of the feedback processes we know of. Before it was always we did simulations with a single feedback process. So it's really cool to see these things. Yes, yes, they take also account. I think to a certain degree, but I'm not exactly sure about the details. Yes. That should be, I think, like on a few tens of mega years. It's normally the timescale in which you form. Yeah. Sorry? It's called Starforge project. It's, I believe, how it's called, Kucic, and I had some people working together with Philip Hopkins. So yeah, he does a lot of this. Yeah, okay, and so we end there. Yes, there you see it. All right. Okay. Now, basically, I mean, to summarize what I want to get across, massive stars are important for two reasons. So on the one hand, they have a very energetic radiation, which can ionize hydrogen. So their radiation is, I mean, hard and ionizing. On the other hand, you have basically their life ends as massive supernova explosions. And what this will do, it injects like thermal and kinetic energy into the medium, so into the interstellar gas. And on the other hand, the supernovae are basically the production sites of all the elements like heavier than from primordial nuclear synthesis. And this is basically how actually, I mean, what we are made of. So we, in a way, we're supernova dust. And I think here, like on the right-hand side, you can also see how it changes. Like when you form the first stars, it's still okay. So, and then you start having this radiation and already clearing like a little bit out the gas. And at some stage, you have the supernova exploding, and then there is not much gas left around the stars. So then you can also imagine once a supernova has really exploded in a region, you won't form there many stars anymore. You might form then stars when the supernova forms sort of shock waves around, then you start maybe forming stars in sort of the edges of the shock waves, because then the gases are more compressed. So the interesting point is then, okay, if massive stars in supernova play such a crucial role, and in particularly how many of these massive stars you have, what does it depend on? So, and here I'm showing results from also radiation hydrodynamic simulations. And what they have done, they have basically looked at gas clouds, and they have gas clouds of different, what we call metallicity. So metals for astronomers is everything heavier than helium. So not the normal interpretation of metals, but yeah. So if you basically have like no metals, that's the very right column. And as you go to the left, your abundance of metals in the gas increases. And then the question is like, how many more massive stars compared to low mass stars do you produce then? Why does it depend on? And what you can imagine, if you have hardly any metals, you only have hydrogen, or mostly hydrogen and some helium. And if you look at the cooling function, what you will find with hydrogen, you can cool down like 10 to the 4 Kelvin. And with molecular hydrogen, to 100 Kelvin. And if you do then a rough estimate with a Jeans mass criterion, you will see, okay, this much of mass can collapse to 1 part, yeah. It's also radiative cooling. So what you will find, if you add more and more metals to the gas, basically you change your cooling functions to lower temperatures. And this is why you start then also forming more low mass stars. And the interesting thing I found like about this recent paper is like they thought also about the CMB background temperature. So what happens if you include the CMB background temperature? And the key thing is if you go to very high redshifts, that temperature is far higher as if you go to lower redshift, so closer to us. Basically, if it's further distance, it's hotter than if it's closer to us. And basically, you see sort of the same trend. For instance, I mean, you see it the best like for the high metallicity case, so the left column. What you can find then, as you go from the top, you basically have the highest temperature. There you will find more massive, relatively more massive stars than if you go basically to today, which is the redshift equals 0. And maybe to quantify this, because I think from this picture it's really hard to see, but these are basically just the simulation results. I mean, if somebody's really interested, sort of the stars here, these basically show you stars, I think, which have at least 10 solar masses, and all the other points are basically stars that are less massive than that. So that gives maybe an idea. But if you want to quantify this maybe a bit more easily, is if we plot. So what we are plotting here is basically on the x-axis we have redshift. So as I say, its CMB temperature increases. And on the y-axis we plot the mass that is in massive stars. So in this case, I think everything that is, all the stars that are more massive than 10 solar masses. And what you can see for the low metallicity case, so that's a blue line, the CMB temperature hardly has any, doesn't make any difference, which makes sense because you can't cool that gas so much down. However, if you go like to the high metallicity case, which is a red line, you actually have a lot of metals which could cool you down. But at early times, you still have the CMB temperature which penetrates the gas. And therefore, you can't cool as efficiently and you still form a considerable amount of mass in high mass stars. So this really changes, if you think about like the more massive stars you're forming, the stronger is your supernova feedback, the more you make the medium turbulent, the more you heat the medium, and the more eventually you might also eject gas from the galaxy and change in the subsequent star formation. So maybe to bring this a little bit more in context. So what do we think of when we talk about, I don't know, galaxy evolution? And I mean, it's a very simplified picture. So you have your dark matter halo. Then you have what we call the circumgalactic medium. That's basically a medium sort of around the galaxy, but mostly, I think, within the boundaries of the halo, although the definitions slightly differ, I think, here. And then we have what we call the interstellar medium. That's mostly where the stars form. And I think what we more or less then call, or what we can see as galaxies. So the processes are basically you accrete gas, the gas cools, stars form. The massive stars explode as supernovae. They enrich the gas with metals. That changes the cooling and therefore the subsequent star formation. So if you have more metals, then you form more low mass stars again. But also because the supernovae inject energy, basically gas is heated and gas can be ejected from the galaxy. And therefore you devoid the galaxy of having gas. And so you're starting to shut down star formation. Now I can wonder, okay, how does it depend on like the galaxy itself or in which gravitational potential it is sitting? So what you can imagine in case of supernovae feedback, if you're sitting in a low mass galaxy, your gravitational potential is rather shallow. So if supernovae are exploding there, they're more likely to push out the gas out of the galaxy. This shuts down basically star formation because either your gas is heated, it's not cool anymore, or it basically evaporates out of the gravitational potential. However, if you go then to a more massive galaxy, they have a deeper potential. So star formation is more concentrated to the central regions. So for supernova, in order to really get it out of the galaxy, they would need to be far more abundant or powerful. So one finds actually that supernova feedback doesn't have much of an effect on massive galaxies. Of course, they regulate to a certain way star formation, but not in the same way as for low mass galaxies. And I think the other thing you can also see here, what happens also as the universe evolves, the mean density of the universe decreases as it expands. So also the shift, like when supernova feedback until which mass plays a role, also shifts slightly as the universe evolves. So if you put this now together, if you were to plot basically the mass on the x-axis and the number density, then you would have your dark matter halos would follow like the dashed line. But what you observe for the galaxies is more like the solid line. And the reason is because here on the low mass end, what you have is supernova feedback basically suppressing star formation. So what you see is then a flattening. And that's basically also what we can observe in the end when we observe how bright a galaxy is and do the number counts. So with this in mind, let's go back to that galaxy evolution is actually a hierarchical process. So you're not only having a single galaxy evolving on its own, but it will also merge with other galaxies. And so in a nutshell, I think to summarize this, as more as a galaxy evolves, the more massive it becomes. On average, it has a higher abundance of metals. It lives in a deeper potential. So, I mean, this is a very extreme summary because I think it's probably most applicable like to the early times. But I think it tells you rather well what's going on. So basically, we go from a metal poor, dominated by massive star in supernova feedback galaxy that has only stochastic, what we call stochastic star formation. What you can imagine is you form stars, then you blow out like the gas. So you don't form any stars, and then you need to wait until you can accrete gas again, and so the gas can cool and form again stars. So what you see is really episodes of star formation in these lower mass galaxies. And at some stage, galaxy becomes so massive that the supernova feedback can't do this, and you basically, in different regions of the galaxies, you continuously form stars. And that's what you then see. And they're also more metal-rich and dominated by low-mass stars because they're becoming more metal-rich. All right. So this was roughly an overview of this. So the question is, like, what do we see? What do we see from these galaxies? And I decided, okay, I focus on, three parts, which I think we also observe. So we have sort of the infrared, the ultraviolet, and the ionizing part of the emitted spectrum. And if you think about, like, then again in this comparison, what do I see from lower mass and more massive galaxies? What you will find in the first case, if you're more massive, you will have had time to produce more metals and then also dust, what we refer to dust. And dust can absorb ultraviolet radiation, and it basically emits in the infrared. And so what you will find then, for low mass galaxies, you probably won't see much in the infrared because they don't have much dust yet. But if you have something very dusty, probably in a more massive galaxies, you will see that in the infrared. If you go to the ultraviolet, it's slightly different. So the low mass galaxies, theoretical, you would see them. They don't have much dust. But if you go to a more massive galaxy that have dust absorbs most of the ultraviolet photons. So then the luminosity, or in the ultraviolet, what is emitted is basically partially absorbed. And yeah, so you need to account, if you look in the ultraviolet, like how much dust does it have at galaxies, how much is it attenuated, in order to interpret like really what, for instance, its star formation is. And the third one, this is actually where I'm working in, is the ionizing, or what I mean with ionizing, hydrogen ionizing radiation. So everything which is above 13.6 electron volt. And what you find here is basically an evolution in cosmic time, whether you will see something or not. So in the very beginning of the universe, you basically don't see any ionizing radiation from galaxies. However, at some point, you start to see them. And this is basically one of the last major phase transition in our universe. And it's called the epoch of reionization. So what happens, all the hydrogen in the intergalactic gas in the entire universe becomes ionized by the very first galaxies in the first billion years. And maybe to understand this in a better way, here is basically a simulation of this. So you will see it's pretty dark, and you'll see now some blue dots. That's basically emergence of the very first galaxies. They emit ionizing radiation, and they start to ionize their environment. And as these galaxies grow and grow, they produce more stars and therefore ionizing photons. And also more galaxies start forming, as you can see, and they do the same. And so the ionized regions start growing as time progresses. And so, yeah, this is basically the epoch of reionization. And I mean, I think reionization makes sense in the sense as we re-ionize the hydrogen after it has formed in the cosmic microwave background, or what we saw there. Yeah, so that's basically one of the state-of-the-art simulations of this. And I think, again, you see here nicely sort of the filamentary structure and so on. Okay. Sorry. So what determines like how this phase transition happened? So if you think about it, there are basically, I think, two parameters that are essential. First of all, how many stars do we form in galaxies? What type of stars do we form in galaxies? How many massive stars do we form then? But then also, if you have this ionizing the stellar population and this ionizing radiation, the question is like, how much of this ionizing radiation actually escapes from the galaxy into what we call the intergalactic medium, so outside of the galaxy. And this very much depends, like, then again, on like how the gas composition and distribution is within the galaxy. And so people, this is hardly, I mean, it's a highly discussed topic, and we actually don't know how much escapes. So this is really up for research currently. And I think people start to think, so what you have again your molecular clouds, where you form your stellar populations in these clouds. Then because you have these massive stars, they emit ionizing radiation. They start ionizing these molecular clouds. And for some molecular clouds, they see this ionizing radiation is large enough so it can penetrate sort of the cloud, and you have the ionizing radiation from the stellar population actually escaping from this cloud. This is also, if you look here, this is basically a snapshot from your simulation. So in the top, you see their cloud. What they show down here is basically what we call the escape fraction. So what fraction of the ionizing radiation escapes into the intergalactic or escapes from the cloud in this case. And the blue is basically your star formation, how many stars you form. And what you see, okay, if you turn on star formation, then shortly after, a lot of the ionizing radiation comes out, and this is because you're ionizing these clouds. But then at some stage, yeah, and of course, if you have a high abundance of massive stars, probably more of these clouds or more radiation can escape from these clouds, because you're more likely, you ionize more of these. But at the end of the life, the massive stars explode as supernovae. And so then your ionizing radiation drops. And initially, basically also your escape fraction drops because the hydrogen starts to recombine. But when these supernovae then explode as their shock waves, you basically clear out the gas channels. And essentially what people find is that once your radiation could destroy your cloud, your supernova explosion will fully destroy it, and the ionizing radiation can just further go on and escape. If the radiation was not really able to destroy your cloud, then the supernova feedback is also less likely to manage it, and actually your radiation is more or less trapped in the cloud. So now the question is also, if you think about the large-scale distribution of less massive, low mass, and massive galaxies, how does this escape fraction depend, for instance, like on how massive a galaxy is? So when you have, for instance, the low mass galaxies, you can imagine, okay, some sort of this radiation escapes from these molecular clouds, goes through the circumgalactic medium, where probably it will be also slightly attenuated, and goes into the intergalactic medium. But if you go to more massive galaxies, then of course you need to pass more gas, so probably your escape fraction will be slightly lower. And also remember, your stellar feedback is less efficient in clearing out these channels. So if you remember, low mass galaxies, we are far more affected by supernova feedback, pushing out the gas. And you won't have that in more massive galaxies. So it's very likely that your escape fraction is then also lower for high mass galaxies. And if one looks at simulation, this is essentially what they're also finding. So on the y-axis, you have the escape fraction of ionizing photons from the galaxies into the intergalactic medium. On the y-axis, you have essentially how massive the galaxy mass. And what you can see, I mean, it's very scattered. So simulations predict vastly different values. But I mean, you sort of can see a trend. It's roughly decreasing the more massive your galaxy becomes. These are two different kind of simulations where you see here more the 2D distribution of all the values that they find. So it's highly variable. And also it really depends on which time of star formation you are. So can we observe this? Not directly, because we can't see the ionizing radiation. So what astronomers do is looking at basically other emission lines. So for instance, you can look at the O3 to C2 ratios. I think also magnesium-2 was looking at. And the other way you can do it, you can observe basically the galaxies close to us, because there you can detect the ionizing radiation. And then you might infer, okay, these are the processes and these are the trends. So if you extrapolate this to earlier times, what would happen? All right, and I think I need to slowly close up. So basically, a bit of the open question that remains today is like, which galaxies basically drove this last phase transition? Was it the most massive galaxies, like on the top panel, where you just have a few massive galaxies creating gigantic ionized regions around them? Or is it like the low mass galaxies, which are more, let's say, evenly distributed, and they form a lot of small-sized regions? And the question is, okay, how could we do this? I mean, one way, I won't go into detail, I think I only mention it here briefly, is basically we look at the Lyman alpha emission from galaxies, because they're really sensitive. Lyman alpha radiation is, as you know, very sensitive to neutral hydrogen. So the more Lyman alpha you will see, the more likely is the larger is the ionized regions around you. But if you don't see any Lyman alpha, it's probably surrounded by neutral hydrogen. But the key problem is also with these lines, they basically redshift pretty quickly out of absorption. So, I mean, I think the bottom line is like, they're actually only sensitive to the nearest, we'll say, one co-moving megaparsec. So in this picture, basically one co-moving megaparsec is like, I mean, these tiny ionized regions here. So that's basically what you're mostly sensitive to. But this is highly complicated because, I mean, the profile of this line is also very much shaped like how the gas is distributed, what is its velocity, and so on, because it's a highly resonant line. Okay, so observing galaxies alone will make it really hard to determine which galaxy population reunites the universe. And so the hope here is on the 21 centimeter signal. So the 21 centimeter signal in this case is the spin flip transition. And so what you will see, it is basically only emitted during the epoch of reionization from neutral hydrogen, or can only be emitted from neutral hydrogen. And this is basically what you, sort of a simulation. So in color, you have what you would see as a 21 centimeter signal. And then you can see the ionized regions growing, and you basically don't see any 21 centimeter signal anymore. And if you measure, we could map this signal, we could follow this process. And this is exactly what radio interferometers are trying to do. And so I have been working also a lot on it, so mainly doing basically statistical analysis on these kind of 21 centimeter maps. So you can do like the 3D power spectrum, where you can see, for instance, here a different simulation with different assumptions, and you can see there's differences. You can look at something like the bispectrum, where essentially then the sign transition over your angle of your triangle in the Fourier space changes as you have. So essentially, if your scenario is dominated by high-mass galaxies, you will find the transition is basically stuck at a certain value when you go through different times. So your universe becomes more and more ionized. It's basically stuck here. While if you driven by low-mass galaxies, sorry, the sign change basically is far more changing, which also, if you look at then the nature of the bispectrum, that actually makes sense. And the third one, I think, which is also very promising, is like cross-correlating the 21 centimeter signal with Lyman alpha emitters. Lyman alpha emitters you only will see when they are in ionized regions. So this is basically a direct measure. How large is the ionized region around a Lyman alpha emitter or a galaxy? And that brings me basically to the end of my talk. I think just mostly telling you the future is really bright for astrophysics. So we are going to learn a lot, I think, in the coming decade. We have all these facilities coming up, basically detecting galaxies across their spectra. I'm pretty sure you have heard about the James Webb Space Telescope having been launched and have given us some very impressive images. This year, Euclid will be launched. I think in 3 years or so, 2 or 3 years, Roman will be launched. It's also in the infrared, and eventually the ELT. ALMA is already observing. That's really more really in the infrared. So this telescope does all the dust absorption. And I mean, finally, in the radio, that's basically targeting the 21 centimeter signal and mapping, let's say, the ionization topology. And here, I think the big hope is a square kilometer array, which the low frequency antennas will build in Australia, and the hydrogen epoch of reionization area, which already has started to observe, but I believe they are going to extend it, so becoming far more. So yeah, with this, I want to end here, and thank you.